Imagine watching 10,000 hours of human cooking videos on YouTube.
Right.
You know exactly what chopping an onion looks like, right? Like, how the light hits the knife, how the pieces fall.
Oh, totally. You've seen it a million times.
But then, imagine trying to actually chop that onion, but your hands have been suddenly replaced by two rigid metal clamps.
Oh, wow. Yeah, that's a nightmare.
And, like, no one has ever told you how to actually move them. That massive disconnect between passively watching a visual action and physically executing it, well, that is the exact bottleneck choking modern robotics.
It really is the biggest hurdle right now.
Welcome to AI Paper Swap. Today we are tearing into a brand new paper. It's called LARA, Latent Action Representation Alignment for Vision Language Action Models.
Published at ICML 2026 by Mengelu and colleagues, yeah.
Exactly. And for everyone out there building robot foundation models, you already know the data wall is just brutal. So we're going straight to the author solution. Give us the 30 to 60 second core technical summary. Like, what does LARA actually do?
Yeah, so for the ML engineers listening, here is the architecture problem in a nutshell. Vision language action models, or VLAs, are bottlenecked because high-quality robot trajectory data is just incredibly rare.
Right, it's super expensive to get.
Exactly. So we try to fix this by extracting action representations from massive human video datasets using what we call latent action models, or LAMs.
But there's a catch there, right?
A huge catch. Historically, we train the LAM and the VLA completely separately, but LARA abandons that decoupled pipeline entirely.
Oh, interesting. So they train together.
Yes, exactly. It jointly optimizes the LAM and the diffusion-based VLA via this continuous latent representation alignment.
Okay, and what does that actually achieve in practice?
It creates this really cool bidirectional regularization effect. So the LAM learns to ignore spurious visual noise, like shadows, while the VLA stops hallucinating functionally useless actions.
Wow, so they fix each other.
Basically, yeah. The result is a plug-and-play framework yielding up to a 15% improvement across major benchmarks, and a 30% boost in fast adaptation to entirely novel robot embodiments.
Okay, wait. A 30% jump for novel robot bodies is a massive claim.
It's huge.
And we are definitely going to put those benchmark numbers under a microscope later. But to understand why this specific architectural fix works, we need to set the stage a bit.
For sure. Context is everything here.
Like, why are we relying on human video in the first place? If you're training a large language model, you just scrape text off the internet. Why is training a VLA so fundamentally different?
Well, the difference really comes down to proprioception and physics.
Right.
Text, images on the internet are already neatly packaged for human consumption, They're symbolic.
They're just tokens.
Exactly. But to train a VLA to control a physical robot arm, you need actual physical action trajectories.
And that's not just a video frame.
No, not at all. That means you need the precise state of the arm at every single millisecond. The joint angles, the torque, the millimeter level gripper position.
And all of that has to be matched perfectly with the visual observation of the environment.
Yep. And you just can't scrape that. Collecting that kind of synchronized telemetry requires running real robots in the real world for thousands of hours.
Or like relying on excruciatingly slow teleoperation by human engineers, which I know is a massive pain.
Oh, it's a total bottleneck. It's incredibly expensive and just physically constrained by the real world.
Which totally explains why the field naturally pivoted to human video. We have data sets like Ego4D with, thousands of hours of humans doing complex manipulation tasks.
Yeah, everyday tasks, opening fridges, grabbing mugs, all of that.
But here is where I get tripped up. There are no precise action labels in a YouTube video.
Right, there's no joint telemetry in Ego4D.
Exactly. You see a human hand grab a mug, but you don't get the joint angles of the hand. So how does a model extract any usable robotic control data from that?
So that's what we call the embodiment gap.
The embodiment gap. Right?
Yeah, because a human hand has soft tissue and, 27 bones? A robot might just have a rigid, parallel jaw gripper. The kinematics just don't translate directly.
So how do we bridge that gap?
To bridge this, researchers use the latent action model, the LAM we mentioned earlier. A baseline LAM bypasses the need for joint angles by essentially trying to predict future video frames.
Okay, wait, so just video prediction?
Basically, by forcing a neural network to look at frame A and predict frame B, you force it to compress the visual dynamics of that movement into a really dense mathematical vector.
And that vector is the latent action.
Exactly. That vector is the latent action. We're operating on the assumption that Whatever mathematical transformation successfully predicts the next frame, well, it must contain the essence of the physical action that just occurred.
Oh, I see. And then those latent actions are served up as, like, pseudo-labels for the VLA to train on later.
That's the standard approach, yes.
But if that works in theory, why are these models hitting a performance ceiling? Like, how does a standard pipeline fail here?
The failure really stems from how these pipelines are engineered in practice. They are multi-stage and totally decoupled.
Decoupled meaning they don't talk to each other.
Right. A practitioner trains the lamb on a mountain of video, freezes the lamb's weights entirely, and then uses it to train the VLA. The lamb is completely isolated from the downstream control objective.
Okay, so let me make sure I'm getting this. Is it kind of like trying to train a language translator by locking them in a room with a dictionary but never letting them actually converse with a native speaker?
Oh, that's a brilliant analogy, yes.
Like, they might learn the rigid definitions of words, but they are totally ungrounded from the actual context of a real conversation.
Exactly. Because the lamb is frozen, it's just guessing what visual features are important based purely on pixel reconstruction. It has no idea what the robot actually needs to accomplish.
Right.
If the lamb's only job is to minimize pixel reconstruction error, it might decide that, say, a shadow moving across a kitchen counter is a highly significant latent action.
Just because a shadow alters thousands of pixels.
Exactly. It has no mechanism to realize that for a robot trying to pick up an apple, the shadow is entirely irrelevant. The visual model is ungrounded from the physical reality of the task.
Wow, okay. Which brings us directly to LARA's core contribution. They throw out that decoupled pipeline and force the LAM and the VLA to share a common mathematical language.
That's the real breakthrough here.
So walk me through how this alignment actually happens under the hood. What does the visual dynamic side look like before we even touch the robot policy?
Sure. So the authors designed a specialized architecture for the LAM side. They use a 4-layer transformer called the M-former.
M-former, got it.
And it doesn't look at every single frame. It processes a temporal stride of frames, looking at visual changes every few frames to capture meaningful movement.
That makes sense, to save compute.
Right. The M-former uses self-attention to distill these temporal visual changes into a continuous latent representation. They denote this vector as Z_T.
Okay, so Z is our continuous vector.
Yes. And here is the crucial difference. In a traditional setup, this Z vector would immediately be quantized.
Quantized, like snapped into discrete buckets.
Exactly. Snapped into a discrete code book with a vocabulary of, say, 128 tokens. And then a 12-layer vision transformer decoder uses those tokens to rebuild the future frames.
So the M-former is compressing the video into this continuous Z vector, and then it usually gets forced into rigid discrete buckets.
Historically, yes.
But before we get to what LARA does with that vector, let's look at the action policy side. The VLA here is a diffusion transformer, a DIT, and it's optimized via flow matching.
Yes, slow matching is key here.
For the engineers listening who might be more familiar with standard autoregressive models, can you unpack what the DIT is actually doing here?
Sure. So instead of predicting the next token in a sequence like an LLM, a flow matching DIT learns a continuous vector field.
A vector field.
Yeah. It takes in the visual observation, the language instruction, and the robot's current state. It starts with pure random noise, and the flow matching process essentially sculpts a trajectory out of that static.
Like carving a statue out of marble.
Exactly. It learns the differential equation that transports that simple noise distribution into the complex, precise distribution of a physical action trajectory.
Okay, so it's drawing this highly complex curve through space, layer by layer. And this is where the paper gets really interesting to me.
Right, the alignment part.
Yeah. Instead of taking the lamb's quantized discrete output and using it as a frozen pseudo-label, LARA intervenes earlier.
Much earlier.
It takes the online continuous latent action from the lamb, that seed vector, before it even hits the codebook, and aligns it directly with the intermediate hidden features inside the VLA's DIT layers.
Yes, and they denote those DIT features as H_T.
Okay, so we have dips from the vision side and HT from the physical side. How do they actually force them together?
The mechanism they use is a cosine similarity loss function, which they call L_LRA.
Cosine similarity, so just measuring the angle between the two vectors.
Exactly. By minimizing this loss, they are mathematically forcing the continuous visual representation, ZST, to point in the exact same direction as the physical action representation, LAHT.
So they're forcibly tethering the visual dynamics to the physical kinematics.
That's a great way to phrase it, yeah.
But, okay, if you're the engineer actually writing the PyTorch code for this, where exactly do you inject this alignment?
That is the million-dollar question.
Right, because a diffusion transformer has multiple layers gradually turning noise into a velocity field. Do you align the LAM features at the very beginning of the DIT or at the final output head?
So the authors ran a really rigorous ablation study to answer that exact architectural question.
And what did they find?
For a base model like GR0000TN1.6, they found the optimal injection point is at layer L-2.
Layer L-2. Okay, why not the very beginning or the very end? What is happening in those specific layers that makes L-2 the sweet spot?
Well, if you try to force alignment in the early layers, those layers are still mostly processing raw noise and basic geometries.
Oh, I see. They don't know what they're looking at yet.
Exactly. They lack the high-level semantic abstraction needed to map to the LAM's visual understanding of the scene.
But then why not the final layer?
Because if you align at the very final layer, the representation has become too specialized. The final layer is hyper-focused on outputting the immediate kinematic velocity.
Like just the raw math of move motor A at this speed.
Precisely. Layer L-2 acts as a bridge. It's the layer where the high-level semantic goal, grab the apple, is just starting to translate into actionable motion.
Oh, that's fascinating. It represents the perfect semantic to kinematic intersection.
Exactly. It's the sweet spot.
That makes intuitive sense for GR00TN1.6. But, we know neural networks are rarely one-size-fits-all. Is this L-2 injection point a universal rule across all VLA architectures?
The authors explicitly warn that it is highly architecture dependent.
Okay, so you can't just copy-paste it.
No, definitely not. When they applied LARA to a completely different model, the Pi 0.5 model, aligning at layer L-2, actually degraded performance.
Like, really? It made it worse?
Yeah. For Pi 0.5, alignment at the very final layer yielded the best results.
Oh, interesting. So the internal feature hierarchies differ that much between models.
They really do. Practitioners have to treat the alignment depth as a hyperparameter to tune. But the underlying principle remains the same.
Which is what?
You generally want to align deeper in the network, closer to the action prediction, rather than in the unabstracted noise processing layers.
Right, that makes total sense. So let's pull back from the layer architecture for a second and look at the actual training dynamics, because this is where the paper makes its most fascinating theoretical claim, I think.
The bidirectional regularization.
Yes. Yeah. This alignment isn't just a one-way street where the LAM tells the LA what the video looks like. Because they are optimized together natively, the gradients flow both ways.
They mathematically discipline each other during training.
Okay, the dual benefit of LAMR. Break that down for us. Let's start with benefit 1, the inverse dynamics regularization for the LAM.
Sure. By anchoring the LAM's latent space to the VLA's action representations, the LAM is aggressively pulled away from learning nuisance variations.
Right. So going back to your earlier example, if a standard LAM is trained on video of a kitchen and a person walks by in the background, the reconstruction loss begs the LAM to pay attention to that person, right?
Exactly. It needs those background pixels to predict the next frame accurately.
But the VLA doesn't care about the person in the background.
Not at all. The VLA is tasked purely with controlling a robot arm to pick up a mug. The VLA's internal features contain zero information about the person walking in the background.
So what happens during alignment?
When the cosine similarity loss forces the LAM's steed vector to align with the VLA's HT vector, the LAM is heavily penalized for encoding that background movement.
Oh, wow.
Yeah, it is mathematically forced to drop the visual noise and encode only the causal control-relevant features needed for physical action.
It sounds almost like they are policing each other.
The dynamic is very similar to that, actually. The VLA acts as a strict filter for the visual model.
So it's literally a neural network buddy cop movie.
That's one way to look at it.
No, seriously.
Yeah.
The VLA is the strict, by-the-book detective who only cares about getting the physical job done. It grabs the LAM by the collar and says, stop getting distracted by the lighting changes in the shadows, focus entirely on the objective.
That's a great analogy. And that buddy cop dynamic goes the other way, too, which is benefit 2.
Forward dynamics regularization for the VLA.
Exactly. While the VLA is disciplining the visual model, the VLA is simultaneously inheriting the LAM's deep understanding of physical state transitions.
So the LAM is the partner looking at the VLA and saying, hey, if you swing your arm that way, You're going to phase through the table, which violates physics. The visual reality doesn't match your math.
Exactly. Because, look, diffusion models are incredibly powerful at generating smooth, continuous curves.
Right.
But without strong visual grounding, they can generate trajectories that are kinematically flawless, but functionally disastrous.
Like drawing a perfect curve that totally misses the mug.
Precisely. We call these hallucinations.
And LARA fixes that.
Yes, because LARA tethers the VLA's internal features to a model that explicitly predicts how objects visually change when manipulated. It heavily penalizes the VLA for hallucinating useless actions.
The action trajectory is forced to remain grounded in the visual reality of the task.
Exactly. It grounds the math in reality.
Okay, mathematically, that buddy-cop dynamic sounds absolutely flawless. But, neural networks are notoriously messy in reality.
Oh, absolutely. Theory is just theory until you test it.
Right? Theoretical elegance doesn't always translate to the physical world. Let's pivot to the hard data. Did this bidirectional regularization actually survive contact with real-world robot hardware?
It did, and the numbers are really impressive.
Because you mentioned a 30% jump in adaptation earlier. And I have to say, hold on, a 30% jump in zero-shot or few-shot adaptation to an entirely new robot body.
I know, it sounds crazy.
In robotics, a 5% bump is usually a paper-worthy win. Are you sure these numbers aren't cherry-picked from some highly constrained, overfit simulation?
Skepticism is totally warranted with numbers that high, but the testing environment the authors set up was rigorously constrained to avoid exactly that kind of hardware confounding.
Yeah, what did they use?
They utilized the Open X Embodiment Dataset, or OXE, specifically focusing on single-arm trajectories.
Okay, so a very standard baseline.
Exactly. By restricting the pre-training to this standardized dataset, we get a clean baseline to see exactly what the LARA architecture is doing, rather than just seeing the brute force results of throwing internet-scale compute at a massive model.
So, holding the pre-training data strictly constant, what happens when you train the full LARA framework from scratch?
Pre-trained from scratch on OXE data, LARA achieves roughly a 12% overall improvement on the Lebero benchmark.
12%.
And a 4% improvement on the simpler ENV benchmark, compared to state-of-the-art baselines like LPA and MotoGPT.
Keep in mind, LPA and MotoGPT are also LAM-based models, right?
Yes, they are. They use latent actions, too.
But they rely on the old, decoupled, pseudo-labeling approach.
Exactly. LARA's joint alignment just mathematically outperforms them on the exact same training data.
A 12% gain on LARA is huge. But, the reality is a lot of ML engineers listening to this don't have the compute budget to pre-train a massive VLA from scratch. They are downloading weights from Hugging Face.
Oh, for sure. Compute is a huge barrier.
So can this architecture be retrofitted, or is it only for ground-up training?
Good news on that front. The authors designed it to be highly versatile. LARA functions exceptionally well as a plug-and-play post-training enhancement.
Really? How does that work?
A practitioner can take a pre-trained base model, freeze the majority of the weights to save compute, and just apply the LARA alignment loss during a post-training or fine-tuning stage.
Oh, that's incredibly practical.
Yeah. They tested this on pre-trained open-source models like GR00TN 1.6 and Pi 0.5.
And what were the results for fine-tuning?
Just by adding this continuous representation alignment during fine-tuning, they squeezed an easy 5% performance bump across the board.
That is a massive win for efficiency.
Yeah.
But we have to circle back to the elephant in the room, the fast adaptation claim.
Ah, yes, the 30%.
Out-of-distribution generalization is the holy grail in robotics. If I train a model on a UR5 arm, it usually fails miserably when I deploy it on a Franca arm.
Every single time.
Right. So how do they test this, and where does the 30% number come from?
They tested LARA on 2 embodiments that were entirely absent from the OXE pre-training data. The GR1 sim in simulation and the real-world G1 real robot.
So totally alien hardware kinematics to the model.
Completely foreign. And in these fast adaptation scenarios where the model is given only a tiny fraction of demonstration data on the new body, LARA drives up to a 30% improvement over the decoupled baselines.
That is staggering. Why does alignment trigger such a massive leap in generalization specifically? Like, what's happening internally?
It's because LARA forces the model to learn embodiment-agnostic action representations.
Embodiment agnostic.
Yeah. When the visual model and the physical model discipline each other, they strip away the hardware-specific quirks.
Oh, I see.
The network stops memorizing specific joint angles and starts understanding the underlying visual physics of a task, the universal geometry of picking up a block, for example.
Right, because physics is physics regardless of what arm you're using.
Exactly. Once a model understands the causal physics of a task, mapping that understanding to a new set of motors requires vastly less data.
And when you zoom out and look at the unconstrained landscape, this result is even more impressive. I mean, LRA, which was pre-trained only on that constrained OXE dataset, managed to outperform massive unconstrained models like Pi, Zero Fast, and Magma in several fast adaptation settings.
It's a huge testament to the architecture.
It's definitive proof that in robotics, architectural intelligence can beat pure scaling. You don't always need a bigger hammer. Sometimes you just need a sharper scalpel.
Exactly. It demonstrates that throwing internet-scale video at a model yields diminishing returns if the model lacks an architectural mechanism to translate that visual data into grounded physical understanding.
And LRA provides that translation mechanism directly in the loss function.
Precisely.
So to synthesize this for everyone building in this space, LRA proves that the bottleneck in robotics isn't just about needing more human video data. We have the video.
We have so much video.
The true bottleneck is ensuring your visual dynamics model and your physical action policy are actually speaking the exact same mathematical language during training.
Could not have said it better myself.
If you leave them decoupled, optimizing them in isolation, you just leave massive performance on the table. Joint optimization through intermediate continuous feature alignment is clearly the path forward for bridging the vision-to-robot action gap.
The bidirectional gradients are the key takeaway. You have to let the physical policy discipline the visual model, and the visual model guide the physical policy simultaneously.
Which leaves me with a final, completely provocative thought for you to ponder as we wrap up today. If aligning continuous latent spaces with intermediate diffusion features is this powerful for bridging vision and robotic action,
what else could we use it for?
exactly. What other modalities could this unlock? Could we use this exact same bidirectional alignment to co-train audio generation models with complex text-to-speech policies?
Oh, that's an interesting idea.
Right. Could we force a music generation model to share a latent space with a physical acoustic simulator?
That would be wild.
If representation alignment forces two disparate neural networks to find a shared causal language and filter out the noise, this might not just be a robotics trick.
It really could be much bigger than that.
Could representation alignment be the ultimate master key for multimodal AI? I mean, it's something to think about. Keep building, keep reading, and we'll see you on the next deep dive into the research here on AI Paper Slop.